Hello, welcome back to three-phase circuit analysis. Here in this lesson, we're talking about the Y-delta single-phase equivalent circuit. If you remember back to the first batch of lessons when we had the Y-Y arrangement, the single-phase equivalent circuit was really the key to doing all of those problems, because ultimately the single-phase equivalent circuit allows you to find, since it's one single loop like this, it lets you find the line current, IA, little a, big A. And when you have that, you can, in the Y-Y arrangement, you can do almost everything else. You can find the voltages everywhere, and then when you have the voltages and the currents, then you can find the other phases just by adding and subtracting 120. So the strategy is going to be the same for Y-delta. We ultimately want to find a single-phase equivalent circuit for that one also. Once we have the single-phase equivalent circuit, it allows us to find that line current IAA, and we'll talk more about it, but ultimately that lets you solve all of these problems, basically. The only wrinkle is that you do not have a nice Y arrangement at the load end, right? You have this delta arrangement. So in the single-phase equivalent for the YY, it made sense that you could do a single loop for the single phase, because if you remember, the Y was one guy, and then the A phase was not in this triangle arrangement. It allowed you to come back through the neutral terminal, and it was a lot more intuitive how you could draw a single phase equivalent for the YY arrangement. It's not so equivalent, it's not so obvious here, because once you get from the source through the line and over here to the load, what do? How do you draw your single phase equivalent? You've got all of these choices here. These are in parallel, plus you have this one. So what do you actually do? How do you draw it? That's what we're going to do in this lesson. That's what we're going to study in this lesson. Now, ultimately, the trick to all of these problems is you want to take your delta load, and I've said it a few times now, you want to transform it. There's a way to transform it into a Y load. And that transformation from delta to Y is very simple, assuming the circuit is balanced. Now, this circuit is balanced because at the load end, Z delta, Z delta, Z delta, they're all labeled the same. That means that these loads arranged in this triangle formation, they're all the same. So this could be 1 plus J 2 ohms. That would mean this would have to be 1 plus J 2 ohms, and this would also have to be 1 plus J 2 ohms. If this one, instead of 1 plus J 2, were 1 plus J 3 or 1 plus J 5 or 2 plus J 1 or something different than the other two, this circuit will be unbalanced, and this conversion to a Y load equivalent is not going to be as easy. You can still do it, but it's not going to be as easy. In this course, we're going to assume all of the loads are balanced. We're doing balanced three-phase circuit analysis. So we want to go from this configuration into something like this. Now, before we go over here, let's go ahead and label a couple of things. Coming into this direction, this is big A. I've got them labeled over here, but let's just, for the sake of clarity, let's call this terminal big A. Whoops, not big A here. This is big B that's connected here, and this is big C. This direction, you have the entire line with the line impedance, and then little a on the other side of the line, and then the source over there. So here we have, looking into this as a black box, if you were to put a dotted line around this, you have three lines coming out, A, B, C, and inside here is some triangle arrangement of loads. And they're all balanced, meaning they're all the same. So what we want to do is we want to convert this into something that looks like this. I'll try to draw it freehand. I'll probably screw it up. But anyway, we want something like this, and then we want to have a common point here, and we want to go here. We want to have a load here, and then we want to have a load right here, like this. Like this, and then this will be right here. And so this will be a terminal, this will be a terminal, and this will be a terminal. And what do you think I'm going to label these? We want to convert from that form to this form, so this will have to be terminal A, this will have to be terminal B, this will have to be terminal C to match up with the three line terminals that we had in the other circuit. And what we're going to call these loads are not the same as the loads in the triangle formation. These are something else that we calculate from that. We're going to call this ZY, because this is the transformed load. Now, I'm not going to prove it to you here, but ultimately it goes back to resistor network theory. If you go back to the basis of your book, we may not have even covered it too much, to be honest with you, because it's not that useful up until you get to this point. But if you have a resistor network arranged like a triangle like this, with resistors, then you can go through the math and you can prove to yourself that you can transform this functionally into this formation, going from delta to Y network, with the following bit of math. Very simple math. The impedance here in the Y shape, ZY, is just going to be equal to whatever that delta impedance in each leg of the delta divided by 3. So very simple. But I need to caution you that this only applies when this is a balanced set here. So if this were 1 ohm, 2 ohms, and 3 ohms, you can't do this. There would be another more complicated arrangement. You'd have to go back through the analysis of looking at delta Y, basically network topologies, to figure out what that would be. But in the special case when it's balanced, which is all of our circuits that we're going to talk about here, then all you do is you look at your delta load. These are all the same impedances. You take one of them, you divide it by 3, and that gives you a new impedance. If you arrange that impedance in a Y shape, where the new transformed impedance goes into here, then from a black box point of view, if you put a dotted line around this guy and cut it off where you have 3 terminals sticking out here, and compare it to what this looks like whenever you put a dotted line around here with the same 3 terminals coming out, you can show mathematically that these two arrangements actually behave exactly the same from a 3-phase analysis point of view. So that's crucially valuable. Why? Because, why? That's a joke, right? Because when you look at this, you don't really know how to write a single-phase equivalent circuit for this, because what do you do when you get here? But if you take this and you put it over here, then again, you have the line connected and you have the source connected over here. Then you have one big circuit and then you have a neutral terminal. Notice there's a neutral here because you've arranged it in a Y arrangement. I'm going to go ahead and put capital N here, there. Even though this is physically constructed different inside the black box, it behaves exactly the same from a terminal point of view, A, B, and C. That means that even though our circuit actually is not a Y load, we can do the calculations as if it were a Y load, because ultimately that's going to give all the same currents and voltages outside of that black box. So this is where 3-phase analysis starts to get a little bit, I don't want to say tricky, because it's not like, you know, general relativity or like quantum mechanics. It's not really difficult to understand, but it is difficult and easy, I should say, to make mistakes sometimes, because you're given a problem in the delta configuration, but in order to make any progress to do the single-phase equivalent circuit, you need to model the load as a totally different kind of load, which is a Y load. So you have to keep in the back of your mind that this Y load here isn't really what's in the box, but it's functionally useful because it helps you build that single-phase equivalent circuit model. Okay? So let's go ahead and draw what that would look like if we were to do that. Let's go ahead and write a single-phase equivalent circuit, kind of in general, what you would actually have if you had a source, if you had a line, and if you had a load. But again, this is the transform load. The actual load that you have is a delta load. Let's see what you would have. So you could write a single-phase equivalent circuit. They're always going to look the same, these single-phase equivalent circuits. So on the source side, we didn't change that at all. We're still talking about a Y-configured source. So we'll have a single source here for the phase A. We'll call that V sub S. And that source has some impedance associated with the windings. We've been talking about that. We'll call that Z sub S because that's the impedance of the source. Then we have over here, we have what we always call little a. And then we have over here some line impedance, Z sub L. Everything up to this point is exactly the same as it is before. Let's continue this on down here below. We're going to say we have a neutral terminal, little n, on the source side, because this is a Y-connected source. And then over here, we have another line, we have capital A. This capital A connection is the same as this one that we're starting to get into what the load looks like now. So what would we have on this side? We have a load impedance. Again, the real load impedance is something called Z delta over there, but we're modeling it by this, so that what's actually in this box for the purpose of this model is something called ZY, which we just calculated. And then we come back here and let's go ahead and connect it down around here. And then this terminal down here, just like all single-phase equivalent circuits, we say that it has a capital N for the neutral terminal. Now I need to talk a little bit about this. The rest of this lesson isn't going to involve any math or any derivations. I'm just going to talk about the process that we use to solve these problems and kind of get all of my knowledge kind of out to you. But ultimately in the next lesson and the several lessons after that, we're going to solve some real problems and you'll immediately see how to do this stuff. But I do want to talk about it for a few minutes beforehand so I'm not doing all of that in the next lesson. So everything to the left of this is exactly as it has been for all of the problems we've ever done. You have a Y-connected source and you have a regular three-phase transmission line. We're only drawing the A phase. So pretending for a second that it was a Y-Y source load arrangement, you have a neutral in the source because that's the common point of all three of the sources coming together. And if we were, instead of building this delta load here, the delta load behaves exactly equivalently as this Y load from a terminal point of view. That means that when we get over here past the line and we draw ZY here, we know that ZY isn't actually what we built. But functionally, from a terminal point of view, it behaves exactly the same. That means that everything inside of this box here, this Y arrangement doesn't really exist. So we're not really going to solve for this, these currents and like circle them as our answers, because the ones inside of this Y arrangement, because the problem doesn't actually have a Y load. But functionally, from a black box point of view, everything to the left is going to behave to the same because we're hooking this equivalent thing on the end. So that means that in our single phase equivalent, don't get tripped up by seeing this ZY right here, and don't get tripped up by seeing this neutral terminal at the load. This is something that confused me a long time ago when I first studied this stuff, because you start asking yourself, well, there is no neutral terminal at the load, so why am I drawing it? Well, you got to just go into Fantasyland for a second and realize that I have a circuit that has no neutral terminal, but it's complicated to model. Because I ultimately want to find IAA, but I don't know how to write a single phase equivalent with all this parallel stuff going on here. So what I do is I take it and I make an equivalent circuit and I put that as its phase A, which in the equivalent circuit there is a neutral terminal here, right? Even though it really doesn't exist for our actual delta load, for our equivalent circuit it's there. So I write it in the equivalent circuit. I have an equivalent phase A load here. This is not the real phase A load, but it's equivalent, okay? And why do I do that? Because ultimately, when I write this as a single loop like this, I'm able to calculate I little a big A. Why am I able to do that? Because this current is going to be equal to the voltage source, whatever it is, divided by all of these impedances. Because for a single phase equivalent, this is just a single loop and you're using Ohm's law to calculate IAA. Now here's the part where you just got to kind of keep it in the back of your mind. You use the single phase equivalent circuit for this kind of circuit just to find IAA, okay? IAA for the single phase equivalent circuit goes right through the line into this, but once it passes this point A, this is fictitious. This was only used as a mathematical tool to find what IAA was. The current really doesn't go into a load called ZY. What really happens is over here, IAA, this is what we found, the current really goes and hits a node of a triangle and splits. So really, in real problems, we're going to be calculating IAA as a first step, because once we have IAA, guess what? We just found a relation in the last section to figure out what the relationship is between the line current and the phase current in a delta load. Remember, it was the square root of 3 and it had a phase shift and all that stuff. So once we have this current, which we can find from the single phase equivalent circuit, we can calculate IAB, that's the phase A phase current, because we have an equation that can shift between currents like this. So then we have this guy. So calculating this is simply a first step. Even if your problem doesn't actually ask you for what the line current is, you're almost always going to have to find it. Because to find this then allows you to shift between this and this. And once you have this current, guess what? You can find VAB, which is the phase voltage VAB, right? So you can do lots of different things. So you have this phase voltage, and then which is exactly the same as this line voltage here. So let's just take a hypothetical. We're going to get into a lot of problems in a second. Let's say you have a circuit. It's a Y source delta load. So we call it a Y delta circuit. Y over here for the source, delta for the load. And we give you some information so that you know kind of what's in the source and kind of how the triangle is configured for the load. And we give you the line impedances, right? And then we say something like, what is the line-to-line voltage? Or maybe we'll say, what is the line voltage, VAB? So you go back over here and you know you have a line and a source over here. You want to find VAB. How would you tackle that? Well, before doing this discussion, you really have no idea how to do it because you don't know how to make a single phase equivalent circuit. But the steps to find VAB would be as follows. You would first take this balanced load, you would divide it by 3, and you would construct an equivalent Y arrangement, so it's equivalently a YY circuit, right? From the point of view of finding the line current anyway. Then you would construct the single phase equivalent circuit exactly the way that we've written it down with this fictitious load impedance here, and then with the other ones in place. Then you would take V over Z, which would let you find IAA. Now you have a phasor current, right? Now you want to know what VAB is. You want to know what this voltage is. So one way to do it is once you know what this current is, you can use the current shift for a delta load, which we just went over in the last section, to then calculate IAB. Once you know IAB, you know the real phase current through this branch of the delta load. And then just with Ohm's law, V is equal to IZ, you would take this current times the known impedance here. That would give you VAB. And since this phase voltage for a delta load is exactly the same as the line voltage, once you calculated this, then you know VAB. Then you would count, you would multiply them, and that would be VAB. That's just one simple example of what you would do. So you use it to find the line current, and then you go about your business doing the rest of the circuit analysis, but you don't get in the trap of trying to say the voltage across the load is actually IAA times ZY. That gets you in trouble. When you try to do calculations inside of this box, that's all fictitious. It's not real. Only the stuff outside is equivalent. So don't try to say, hey, the voltage across, the VAB or something like that is the voltage across this phase of the load, because this phase of the load isn't real. It was just a mathematical tool. All right, enough talking. I think I got most of the points out. Let's go on to the next section. You'll see very quickly how to do this stuff, and you should be able to inch your way from problem statement to solution pretty easily once we have a general map like this to tackle these kinds of problems.